Today we're going to be discussing oxidation numbers. Oxidation numbers are another way to describe the number of electrons involved in a chemical reaction. So you can see our objective today is to be able to identify or determine the oxidation numbers for each element in a chemical compound. A couple statements here that we can hold true that we know a little bit about. The oxidation numbers or oxidation states can be the same value as an element's charge. It describes an electron's movement. These oxidation numbers are very important in describing those 7 nonmetals listed because they have several common oxidation numbers or oxidation states. Again, it talks about the number of electrons involved within each atom, and ultimately by identifying the oxidation number for atoms in a chemical, we're going to be able to realize that from one chemical to the next, the oxidation numbers of an element can change. Now what this allows us to do is a simpler way to figure out how many electrons are involved in the chemical bonding process. Back in chapter 6, one way that we would have done this would have been to identify the Lewis structures for these two chemicals, SO3 and SO3 2-. So what I want to do is a quick review here. Give you about 5 minutes here. I'm going to pause it, allow you to work on this. So you pause it. Come back and we're going to look at the Lewis structures for these two chemicals and kind of do a couple different things with them that leads into oxidation numbers. Okay, we have the two Lewis structures for SO3 and SO3 2-. Now the first thing we want to start out with is the electron dot of sulfur. We see the electron dot of sulfur. There are 6 electrons that a sulfur atom has. Now what we want to do is we want to look at what is happening in the bonding process. If we see here in the sulfur, we notice that there are no electrons that are left unpaired or unshared. So what that's telling us is all 6 of sulfur's electrons are involved in the bonding process. That number 6 is important. If we look at our other example, again, sulfur has 6 electrons in its original dot structure, but it has 2 electrons it did not have to share in the bonding process. So the number 4 is significant. So what we really want to get out of this is the numbers 6 and 4 without actually having to draw Lewis structures to accomplish that. This is important because it does tell us a lot about how they're bonded, the shape of these molecules, the electron arrangement, polarity, London forces, dipole forces, and all those types of things. But if we're just trying to figure out what the oxidation number is, we really don't care how they're put together, we just want to know how many. So as you look on the first page of the section, here are the different rules and statements that apply. And as you can read through these, most of these make pretty much sense. Fluorine we've talked about, -1. Hydrogen, +1. Oxygen, -2. Metals, oxidation number is the same as their charge. The last 3 statements are really the critical ones so that we can understand how to calculate the oxidation numbers of other elements. As you can see here, the sum of all the oxidation numbers in a compound must add up to be 0. The sum of all the oxidation numbers in an ion has to equal its charge. And if we're not sure what an oxidation number should be, if we can't decide between 2 elements, then the one that's the most electronegative is the dominant element. Therefore, its oxidation number is equal to its charge. So if you want to, you can pause these for a few seconds or obviously copy them out of the book. What we're going to do next is sort of take those 2 chemicals, SO3 and SO3 2-, and really calculate this by setting this up like a chemical algebra equation. So what we're saying here is the oxidation number of sulfur plus the oxidation number of 3 oxygens has to equal 0. Over here, the oxidation number of sulfur plus the oxidation number of 3 oxygens has to equal -2. So if we go through these and again solve for S in this case, we know the oxidation number for oxygen is a -2 based upon its rules. So going through and solving these, again, you can follow along in the algebra here. Now, if we look at the significance here, of +6 and +4. By doing a little bit of algebra, we were able to find our values of 6 and 4 without having to draw Lewis structures. That's all we're trying to do here. The significance of oxidation numbers. Let's say we have a chemical reaction that somehow converts SO3 to SO3 2-. This is what we call a redox reaction. This is the beginning stages of electrochemistry. All right, so what I've got here is I'm going to give you 4 more examples. I want you to kind of work through these 4, see if you can see what the oxidation numbers are, and then be able to kind of wrap this up. So I'll pause this here. You can too. Okay, as we wrap up here, we've got 4 more chemicals. H2O. As you go through and solve oxidation numbers simply by the rules, hydrogen is a +1, oxygen is a -2. In the CO3 2-, you can go through, follow through the algebra. We know by the rules oxygen is 2-, therefore carbon is a +4. In our other 2 examples, we have barium sulfate. Okay, a barium plus a sulfur plus 4 oxygens is going to equal 0. So knowing barium's charge is a +2, that's its oxidation number. Go through, solve the algebra. Sulfur's a +6, barium's a 2, oxygen is a 2-. And the last example, carbon dioxide. Oxygen's a -2. Solve through the algebra. We therefore know carbon is a +4 oxidation state. Oxygen has a -2 oxidation state. Just as a reminder, again, these 7 nonmetals have multiple oxidation numbers. So they're the ones that we want to solve for last. So as you go through that process, those are the ones that you want to solve for at the end. Figure out all the other ones first, and then end up solving for them. As you can look on page 235 at the top, there I have table 6 common oxidation numbers that have variable oxidation states. Last example I just want to give is, what if we have a metal that could have multiple charges? You know, how do we know what our oxidation numbers are going to be? It's going to be 2, 3, or 6. Well, simplest way, just uncross the subscripts just like we would have gotten a formula. In this case, we know it's iron 3. Another way we know it is, well, if it's Fe2SO4 3, we know the sulfate's a 2-. It took 3 of those to be a -6. Therefore, the iron has to be a +6. Each iron has to be a +3. Therefore, we know it's iron 3. So Fe plus sulfur. Now again, you have to watch our formula here. It's 3 sulfurs plus 12 oxygens. Taking the entire formula, and we actually have 2 irons. So solving through here, we're going to see that S equals +6, Fe equals +3, and oxygens equal -2. And that concludes the lesson on oxidation numbers.